So let's derive the fundamental property relations and Maxwell's relations in thermodynamics using only a single square. So this is my square. I will write the thermodynamic properties S, U, V at G, P and H. S stands for entropy, U stands for internal energy, V stands for volume, A stands for Helmholtz energy, T stands for temperature, G stands for Gibbs free energy, P stands for pressure and H stands for enthalpy. So now I will draw two arrows, one from pressure to volume, another one from entropy to temperature. So this is the complete square. Now in order to remember this SUV at GPH, I have a sentence. These are known as mnemonic. These are used to remember a certain sequence. So this is the sentence that I have: Sun, Uranus, Venus at Green Palace Hotel. So from Sun I will take the letter S, from Uranus I will take the letter U, from Venus I will take the letter V, at I will take both the letters A and T, from Green I will take the letter G, from Palace I will take the letter P, and from Hotel I will take the letter H. So likewise you can remember SUV at GPH by remembering this sentence only. Now only with this square and this sentence we can derive all the fundamental property relations and Maxwell's relations. So first I will try to derive the fundamental property relations. So first I will start from this internal energy U. So I will write du is equal to, so in the adjacent sides of U I have S and V. So I will write ds and dv. Now in the corners of S and V, in the opposite corners of S and V I have T. So I will write T in front of ds, and in the opposite corner of V I have P. So I will write P over here. Now fun thing, in S I have the tail of this arrow. So tail indicates positive and head indicates negative. So same goes for here. The tail indicates positive and this head indicates negative. So for S I have the positive side, so it will be positive, and for V I have negative, so it will be negative. So the first fundamental property relation is du equals to T ds minus P dv. This is the first fundamental property relation. So next I will derive for enthalpy, which is H. So dH is equal to, so again in the adjacent of H I have S and P, which is entropy and pressure. So I will write ds and dP. Now in the opposite corner of S I have T, so I will write T over here, and in the opposite corner of P I have V, which is volume, so I will write V over here. Now for ds, in S side I have positive, which is the tail, so I will give a positive sign, and on the pressure side I also have a positive sign, so I will give a positive. So this is the fundamental property relation for enthalpy. Next comes the Gibbs free energy G. So this will be written as dg equals to, now in the adjacent sides of G I have pressure and temperature. So what I will write is dP and dt. Now in the opposite corner of P I have V, so I will write V over here, and in the opposite corner of temperature I have S, which is entropy, so I will give S over here. Now you can see that P, in the pressure side I have positive, so I will give positive, and in the temperature side I have negative, so it will be negative. So this is another fundamental property relations which says dg equals to V dP minus S dt. So I will box this also, which is for the internal energy, du equals to T ds minus P dv. So last what is remaining is the A, which is the Helmholtz energy. So for Helmholtz energy I write it as dA equals to, again in the adjacent sides I have volume and temperature, so this will be dV and dt. Now in the opposite corner of V I have P, which is pressure, and in the opposite corner of T I have S, which is entropy. So now the sign for V, for volume, which is dV written over here, I have a negative sign, so I will give negative, and for temperature I also have a negative, so it will be minus P dV minus S dt. This is the fundamental property relation for Helmholtz energy. So these are the four fundamental property relations which I have derived using this square. Now I will derive the Maxwell's relations using this same square. So I have the same square which I had to derive the fundamental property relations. Now I will use this to derive the Maxwell's relation. So I will write the properties only at the corners, that is S, V, T and P. So entropy, volume, temperature and pressure. The arrows are in this manner. So for the first Maxwell's relation, what I have is dP dt del P del T at constant volume. So I am going from P to T at constant volume. So this is the left hand side of the equation. So to write the right hand side of the equation, what I will do is I will travel the opposite side. That is, I started from P, now I will start from S to the opposite side. So del S del V at constant temperature. So now the sign of these terms. So del P del T at constant V, this follows this arrow, hence it will be positive, and del S del V at constant temperature follows this arrow, this follows this arrow, hence it will also be positive. So this is the first Maxwell's relation. So to derive the second Maxwell's relation, I will start from temperature now. First I started from P, now I will start from temperature. So what I will go is, I will go from T to V followed by V to S, V to S. So what I will have is del T del V at constant entropy. This will be equal to, now since I started from T, I will now start from the P, which is the adjacent opposite to the ones I started in the first. So del P times del S at constant V. So I have traversed from P to S followed by V. So this is in accordance to this arrow. Del P del S at constant V is at this arrow, hence it will be positive, and del T del V at constant S is in this direction, which is opposite to this arrow, hence it will be a negative. So this is the second Maxwell's relation. So for the third relation, I will start from volume and go to entropy followed by pressure. So this will be del V del S at constant pressure, del V del S at constant pressure. This does not follow this arrow, it is in the opposite direction, hence I will give a negative sign. So this will be equal to, so since I started from V, now I will start from temperature for the other side of the equation. So del T del P at constant entropy. So now you can see that I went from T to P followed by S. This is also in the opposite to this arrow, hence I will have a negative in both the sides of the equation. So negative will be cancelled out, and what I will have is, so this is the third Maxwell's relation. Del V del S at constant P equals to del T del P at constant entropy. So next is the last one. So for the last one, I will start with S and traverse in this direction, S to P followed by T. So what I will have is del S del P at constant temperature. This will be equal to del S del P at constant temperature. This follows this arrow, so it will be positive. So this will be equal to, so now I will start from V and del V del T at constant pressure. So I went from V to T followed by P. So this is in the negative of this direction, hence a negative sign will be put. So this is my fourth Maxwell's relation. So these were the four Maxwell's relations. Thank you.